Hello pre-calculus. Today's video is going to be basically me reviewing the answers to everything from day 131's assignment. And really all I'm going to do is talk about continuity and this funny little question about what are the c values for which the limit as x approaches c of f of x equals 1. Now this should be super helpful for day 132. It's an assessment that's just basically saying, hey, do you know what you're doing with finding limits, graphically talking about continuity, and just, having a good feel for everything. So getting to it, if I'm looking at this first function for number 1, let's talk continuity first. So remember, continuity can be categorized into two different fields. One is non-removable discontinuities, two is removable discontinuities. So talking about the non-removable ones, so this graph is non-removably discontinuous, this function right here, at all the places where the limit does not exist. So when you think about it, where you see an asymptote, that's a place where a limit does not exist. So right here, you can see we've got an asymptote. From the left, it's going to negative infinity. From the right, it's going to positive. So at x equals 1, 2, 3, negative 4, you've got a non-removable discontinuity. So we're going to say NRD, non-removably discontinuous at x equals negative 4. That's the only asymptote. Now, there's also a place where if you've got a break in the graph, and what I mean by a break in the graph is not necessarily a hole like you see here or here, because there's almost a continuity that continues. You go to the hole. At this point, it jumps down, but it pops right back up and continues on there. This one doesn't even have an extra spot to jump down to. It's almost like there's a pothole there. It hops over it and then just goes right back down. This is what I am describing as a break in the graph. All right, it's a place where it basically cannot be bridged by just filling in one particular point. So there's a non-removable discontinuity at x equals 1, 2. Because of the break at x equals 2. Okay. So the next one would be, where do we have removable discontinuities? So remember, this is a place where the graph is discontinuous, but the limit does exist there. So when you think about it, it's like, what are the points where the limit from the left the limit from the left equals the limit from the right, and it converges to a specific spot. Well, right here looks like a prime candidate. The limit as x approaches 1, 2, 3, 4, 5, 6 from the left is equal to 1. The limit as x approaches 6 from the right is also equal to 1. So this point right here, this is just the function's value at 6. This is f of 6. F of 6 equals negative 1. But the limit as x approaches 6 is 1. So, because the limit exists there, it is a removable discontinuity. And then the same thing happens at 8. Since the limit from the left matches the limit from the right, they're both equal to 1, 2, 3, 4, 5, 6. Then that one's also a removable discontinuity. So there's your answer. So continuity, it's pretty basic once you get the bottom line rules down. This one can be tricky at times, and you'll see right here for this example. The limit equals 1 where? So here's what I would do to start. I would just say, creating a horizontal line at 1, you're focusing on only those values when from the left and the right, the limit converges to 1. So let's think about this. From here on, there's nothing beyond the graph that actually would lead us to believe that this limit would ever approach 1. See, it's leveling off at 2 right here, and it's not coming back down. However, right here, the limit from the left equals the limit from the right. So that would be a point that we would contend, yes, that is a place where the limit equals 1. So it would be from the origin, 1, 2, 3, 4, 5, 6. So at negative 6, C, the limit as x approaches negative 6 of f of x equals 1. All right. So when we're talking about C, an interesting way of putting notation to it is putting curly braces. You might see this every once in a while in a math textbook. So the curly braces there just to indicate negative 6 is one of the x elements that belongs in this category that we're talking about right here. Now here's the next part that'll blow your mind. So nothing really important here. That's important. We have it documented. Nothing important, but right here, this is the spot where it's like, whoa, we got a bunch of different points in between here where the limit is equal to 1. So what do we do with that? Well, the first thing we have to establish is, what about x equals 2? Is x equals 2 a legitimate candidate for this? And the answer is no, because the limit from the left is about 2 1/3. The limit from the right is 1. They don't match up at that spot. However, at 2.0000000001, just to the right of 2, the limit from the left of that and the right of that does converge to equal 1. So basically at all these different spots, you're talking about C. Those are places where the limit equals 1. So what we do is we say, we're going to include all of these values in between 2 and 1, 2, 3, 4, 5, 6. So we're going to put interval notation inside the curly braces. I'm going to put a parenthesis here because we're saying we're excluding the value 2 because the left and right limits of those do not converge to a specific value. But we are going to include 6 because the limit from the left of 6 is equal to 1. The limit from the right of 6 is equal to 1. So that value should be included with a bracket. And then lastly, 1, 2, 3, 4, 5, 6, 7, 8 point, I'm going to say 8.6. That is a value that doesn't have like a little closed bubble or an open circle to indicate that that's like a point of contention. But these line segments or these curves are basically a bunch of individual points that have basically been filled in to create the curve itself. So this there, I just made it a dot that has 2 dimension to it so everybody can see it. That's a point that we include in that little, just in this scenario of the values that C should equal. So I'm going to put it down here. I don't know if you guys can see it on the screen there. 8.6. Curly braces closed. That technically should be your answer for number 1. I'm not sure too many people had that written down as that, but yeah, it's cool to know that the interval notation we talked about earlier is starting to really take shape with really a calculus concept that you see here with limits. Let's check out number 2. So I kept things the same. Continuity, limit, even equaling 1 was the task at hand. This one's a lot easier to deal with. Continuity. So right here, this is a closed dot. So it is not discontinuous at that point. This is a closed dot. This should be a closed dot as well. Sorry, the copier sometimes is mayhem for this kind of thing. These are the 2 spots where we are discontinuous, as well as this point in between them because, of course, it has an asymptote. So we have a non-removable discontinuity at 2 because it's an asymptote. And make sure you guys are putting NRD for non-removably discontinuous or RD for removably discontinuous. Don't just not put anything in place of it. And then these two are both removable discontinuities. Notice, removably discontinuous functions are not changed based on the fact that there is a closed circle here, like a specific x value that corresponds to an actual y value dot, that doesn't change the removability of a discontinuity. They're both removably discontinuous. So at x equals 1 and 1, 2, 3. Okay? Now, where does the limit as x approaches c of f of x equal 1, what's the c values that make that true? So if we just thought about our imaginary horizontal line of 1 as its y value, so it's like nobody, 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 nobody here. All right, so at x equals -1, to the left of that, from the right of that, even if it's a closed dot, it still has properties that say, hey, you have the right to a limit. Every x value on here has a right to a limit, or at least a right to you trying to figure out what the limit is from the left and the right of that. So -1, that limit, or that x value, is legit. X equals 1. That's the same thing. From the left it equals 1, from the right it equals 1. And then at 3, it also converges to 1 from the left and the right of that point. 1, 2, 3. Let's see. I've got about 3 minutes in this video. I'm not sure I can finish the whole thing up without running out of time. I'm going to stop this video, and we'll start back up on a new one.